The universe is cooling. Not metaphorically. Not symbolically. The literal temperature of space, once so hot it could burn holes into atoms, is fading into something colder than silence. Begin with a poetic, cinematic narration of a photon traveling through the thinning cosmic microwave background, stretching into longer wavelengths, losing energy, fading into darkness. Time slows. Expansion accelerates. The universe drifts toward heat death. Introduce the central idea. The universe is cooling faster than expected. Much faster. And buried inside this fading cosmic temperature is a question that challenges cosmology, entropy, dark energy, and the ultimate fate of space itself. End with a cold, reflective line. If everything is falling into stillness, what is left for the universe to remember us by? In the early 1960s, the world moved beneath ordinary rhythms. Cars roamed the highways, radios hummed with distant voices, and the moon waited for human footsteps. Beyond those small motions, beyond atmospheric winds and quiet earthly mechanics, the universe itself concealed a remnant of its birth. It traveled through space as a faint warmth, a temperature not of sunlight, not of stars, but of creation itself. And no one had yet heard it. At Bell Telephone Laboratories in New Jersey, a white horn-shaped radio antenna pointed toward empty sky. It had been designed to listen to satellite echoes, to capture signals bouncing across the atmosphere. Its engineers expected static, distortion, everyday terrestrial noise. But the instrument returned something else, something soft, steady, and strangely uniform. It did not matter where the antenna pointed, the signal remained. It was faint but persistent, and it carried a temperature. That temperature was measured at roughly 2.7 Kelvin. Not zero. Not nothingness. Not silence. A warmth still alive. Arno Penzias and Robert Wilson initially believed the anomaly must be contamination. They examined coaxial cables, recalibrated receivers, cleared pigeon nests from inside the antenna, and washed away microscopic traces of droppings, thinking even fragments of dust might be corrupting the signal. But the faint radiation remained. It filled every direction. There was no escape from it. The universe itself was glowing. The glow represented heat, heat no longer burning, but decaying, heat that originated from a universe once impossibly hot. Across those early measurements came the realization that space was not black. It held residue, memory, embers suspended across billions of light years. That warmth was later defined with precision, 2.725 K above absolute zero. A temperature so small that liquid helium still boils fiercely above it. A temperature colder than any deep crater on the moon. A temperature not belonging to any star, nebula, or galaxy clusters, but belonging to the beginning of time. To understand what was detected, cosmologists turned backward. They reasoned that the early universe, moments after the Big Bang, had reached nearly 10 billion Kelvin, a realm where atoms could not exist. Pure plasma, charged particles, and radiation filled space, tightly confined by density. As time expanded, matter cooled. When 380,000 years had passed, an era known as recombination, the universe reached roughly 3,000 K. Hydrogen formed, light separated from matter, and photons finally began traveling freely. Those same photons now fill modern space. They have stretched, cooled, and faded. What Penzias and Wilson heard was fossil light. A thermal afterglow left behind by everything becoming less violent. It swept across sky maps as uniform brightness, a nearly perfect blackbody distribution, and that uniformity became the greatest shock. Because nothing in astrophysics had shown such equality. Stars differ, galaxies differ, clusters differ, but this signal did not vary. It was present everywhere. It came from all directions equally, meaning nothing local produced it. The radiation existed at cosmic scale. Within 2 years, cosmologist Robert Dicke announced that the discovery aligned with predictions dating back to the 1940s. Predictions that the universe must contain leftover thermal radiation. But no one expected the signal to be this constant, this pure, this unmistakable. In lecture halls, chalk traced lines showing how expanding space should dilute radiation. Wavelengths stretched, temperature fell, energy thinned. The numbers matched perfectly. Cosmology changed abruptly. Those measurements convinced scientists the universe was cooling, a process not symbolic, but physical, driven by expansion. It meant the Big Bang did not simply occur, it continued unfolding, losing heat every moment. If space stretched, radiation lost energy. If radiation lost energy, temperature fell. And it did not fall gently. It dropped across epochs. From billions of degrees to thousands. From thousands to just above zero. From brightness to almost total darkness. The faint sound in that antenna was a horizon of warmth separating the universe that once existed from the universe forming now. Later missions would refine the value, improving instruments, filtering atmospheric interference, deploying receivers above Earth entirely. Satellites like COBE, WMAP, and Planck would eventually measure the cosmic microwave background to microscopic accuracy. But before those orbital observatories came the first realization: the universe was not dormant. It was cooling. Before this detection, cosmology struggled to prove its earliest claims. The Big Bang was often debated alongside steady-state theories. Models proposing that matter formed continuously, filling expanding space and preserving perpetual uniformity. But the remnant heat revealed evidence of a beginning. No steady-state model could produce that temperature. No eternal equilibrium could sustain such relic radiation. Heat, by its nature, fades. That fading implied a start. The universe had once burned. Measurements revealed the texture of cosmic infancy. They showed that time does not simply move forward, it cools. Energy disperses not into destruction, but into stillness. The cosmic microwave background became a thermometer, not just of temperature, but of age. To measure its heat was to measure the cosmos itself. Scientists concluded that if the universe held a temperature today, then it must have been warmer yesterday, warmer still a million years before that, blazing at the moment of origin. Suddenly the future of space appeared not as endless creation, but as gradual dimming. Heat would continue lowering. Objects would drift apart. Radiation would stretch infinitely. Everything would soften into equilibrium, but a quiet equilibrium, not a dynamic one. The universe was revealed as a system still losing energy, still moving toward a deeper chill. Penzias and Wilson did not see that far ahead. Their discovery was confined to data, noise patterns, instrument behavior. Yet embedded in that noise was something vast. Cosmologists later described this realization as the beginning of modern cosmic thermodynamics. Temperature became a timeline. The microwave background became a funerary glow for what creation once was. And there was something almost poetic in knowing that every star, every atom, every structure in existence emerged in relation to this temperature decline. Matter condensed because cooling allowed it. Galaxies formed because density could increase. Stars ignited because gravity could overcome expanding heat. The universe is not merely cooling. Cooling is what wrote its architecture. That first faint signal, humming through a white metal antenna, carried the future of cosmology on its wavelength. Once measured, humanity knew. Space would not stay at 2.7 Kelvin. It would fall toward zero. Not rapidly, but inevitably. With each passing epoch, photons lose energy. Light stretches until its frequency is so weak it can no longer warm even the smallest particle. Expansion thins radiation until barely anything interacts with anything else. And the temperature that Penzias and Wilson measured, though astonishingly small, is not final. In laboratories, scientists began calculating what would happen in billions, trillions, or quadrillions of years. The result was stark. Stars would go dark, galaxies would disperse, and the universe would become a domain defined not by movement or illumination, but by low energy. A place where cosmic warmth becomes rare enough to count individually. The discovery marked the first glimpse into the dying temperature of space. The moment the signal became known, cosmology shifted from creation narrative to cooling trajectory. The universe was not racing upward in complexity, it was dissolving downward into simplicity. That faint radiation was not just a measurement, it was a direction. Humanity had found evidence of a universe already fading. And in that fading warmth, a question settled across scientific imagination. If temperature is the memory of the beginning, how long will the universe remember it? How long before the final remnant disappears into silence? Across the vast cosmic span, space does not merely sit as a silent container for energy and matter. It evolves. It stretches. It changes shape. And with each subtle widening, a profound transformation spreads through everything suspended within it. In the early 20th century, Albert Einstein proposed an idea that seemed, at first, almost too abstract to belong to the physical world. That gravity was not a force pulling objects together, but the bending of space and time themselves. General relativity described a universe not fixed in shape, but one capable of changing its structure. And years later, observations of distant galaxies revealed the astonishing implication of that idea. Space was not static. It was expanding. In a world governed by common intuition, expansion is simple. A balloon inflates. A tide recedes. A field stretches across land. But the expansion described by Einstein, and later observed through telescopes, does not operate within space. It stretches space itself. Galaxies do not move outward through a cosmic arena. The arena itself grows between them. And with that expansion arrives an effect so subtle yet so powerful that it reshapes the destiny of the cosmos. Every photon of light, every particle of energy born in the first moments after the Big Bang, travels through a universe that is continuously stretching beneath it. And as space stretches, light stretches with it. A beam that once burned bright and hot lengthens into a colder wavelength, losing energy not through collision, not through friction, but simply by traversing an expanding cosmos. This slow fading is known as cosmological redshift. Light that once carried heat is diluted. Light that once burned like white flame becomes quiet. As its wavelength stretches, its energy weakens. The early universe glowed with temperatures unimaginable today, millions of degrees across regions the size of galaxies. But as expansion relentlessly continued, that radiance stretched itself thin. Today, what remains of that ancient blaze is the cosmic microwave background, cooled to just above absolute zero. And tomorrow, if measured across cosmic scales, will be colder still. There is no resistance in this process. No force pushes back against expansion. Space does not rub against itself. The fading of light does not slow. There is no mechanism, physical or conceptual, that reverses that energy loss. It is a one-directional decay. In thermal physics on Earth, heat flows from hot to cold until balance is achieved. But in the universe, that equilibrium is not possible, not because temperatures do not equalize, but because the very fabric of space drains energy away faster than any physical structure can restore it. The result is a future defined not by decay in matter, but decay in temperature itself. The cold deepens. The universe cools not by releasing heat outward, but by stretching inward from the scale of spacetime. As radiation loses energy, its ability to warm matter fades. What was once thermal interaction becomes distant echo. What was once radiant power becomes a silent whisper of the past. And with this cooling comes a paradox. No known physical process allows the universe to warm again. On Earth, fire heats stone. Stars ignite hydrogen. Chemical reactions release warmth. But all of these processes occur inside a container, the universe itself. For the cosmos as a whole, there is no larger container. No external source. No reservoir of energy waiting to return. General relativity predicts that if expansion continues, especially accelerating expansion, photons will redshift until they no longer meaningfully participate in the exchange of thermal energy. They will stretch beyond visibility, beyond interaction, beyond usefulness. At some distant age, every photon emitted by every star will be so redshifted that it will no longer carry heat. Space will continue expanding even as radiation thins toward nothingness. This is not decay in the classical sense. Nothing breaks apart. Nothing dissolves. Instead, energy fades into scale. A universe cooling not because matter changes, but because geometry enlarges. The paradox deepens further. In thermodynamics, equilibrium marks the end point of energy flow. But equilibrium assumes scale remains constant. It assumes space itself does not rewrite energy. That assumption fails when relativity controls the outcome. The universe will never reach equilibrium. Because every time light approaches even distribution, space expands again, stretching that distribution thinner than before. The cosmic temperature falls not toward rest, but toward asymptotic silence. Almost zero, but never reaching zero, almost heatless, but still holding the faint memory of ancient fire. Scientists studying this process project the far future in curves, not sharp declines, but smooth slopes descending across trillions of years. The cosmic microwave background will slip beneath detection long before stars die out. The sky will darken, not from absence, but from energy stretched into invisibility. Every galaxy beyond local gravitational clusters will drift beyond the edge of cosmic horizons, not moving away, but moving out of sight behind the expanding fabric of space. As photons lose energy, time itself appears to soften. The glowing imprint of the Big Bang, once vivid and violent, becomes a quiet residual hum of existence. Like embers fading beneath cold ash, the background radiation becomes less a light and more a memory. Even the idea of temperature becomes fragile. Temperature depends on energy exchange. When radiation no longer transfers heat, temperature itself loses meaning. Matter approaches thermal isolation. Stars no longer receive background warmth. Dust no longer glows faintly in cosmic microwave light. Planets, if they still exist, will be too cold for chemistry to respond. The universe continues expanding, but nothing changes inside that expansion. No new energy cycles form. No large-scale heating returns. Once energy spreads thin, it does not gather again. This is the irreversible outcome of redshift. A cosmic cooling without rebound. The paradox rests here. The universe was born in heat. The universe moves toward cold. But cooling eliminates every mechanism that might reverse this trend. There will be no cosmic reheating, no new ignition, no large-scale thermal migration toward warmth. The expansion itself, not time, not entropy, not decay, is what prevents temperature from ever rising again. This is why cosmologists refer to the long future not as darkness, but as thermal isolation. Stars die not because gravity weakens, but because fuel is finite. Temperature fades not because something consumes it, but because empty space stretches beneath it. And so, the universe ages in silence, not through collapse, not through destruction, but through expansion. This is the strange contradiction encoded in relativity. The universe expands freely, but that freedom sentences radiation to fade. And that fading defines the future. Somewhere, in the distant epochs beyond measurable time, a final photon continues stretching, a last remnant of a universe once radiant and hot. It travels through space still expanding beneath it. Its wavelength grows. Its heat dissolves. And eventually, that photon becomes indistinguishable from vacuum itself. A moment will come, across cosmic durations, when matter no longer remembers warmth. The universe will not be dark. It will be cold. A universe that began with violent light will end not in collapse, but in imperceptible quiet. Not extinguished. Simply expanded beyond the reach of heat. When the cosmic microwave background was first confirmed, its discovery offered relief. The universe, once an untouched blank, finally revealed evidence of its youth. Scientists expected the radiation to be smooth, perfectly uniform, perfectly symmetrical, perfectly balanced. A universe that expanded evenly should cool evenly. A cosmic glow spread across all directions should contain no distinctions, no texture, no gradients. For a moment, it almost appeared that way. Early measurements hinted at symmetry. The temperature was astonishingly consistent. Every region of sky displayed nearly the same value, measured at roughly 2.7 K. But the deeper analysis began revealing something unexpected: imperfections. Subtle ripples. Minute disturbances across wavelengths so delicate they could barely be resolved. In theory, The universe should not possess these variations. Cosmology expected uniformity. Instead, it found wrinkles. Those wrinkles were small, so small that the human body could not sense their difference. A fluctuation of only about 1 part in 100,000, hidden inside frequencies that had stretched for more than 13 billion years. One region was slightly colder than its neighbor. Another held heat just fractionally above the cosmic average. On printed graphs, the variations looked like static, mere noise. Yet the noise was real, and it carried meaning. The first suggestion of these fluctuations emerged from painstaking charting. But confirmation did not arrive until NASA launched a satellite designed solely for this purpose. It was called COBE, the Cosmic Background Explorer. When COBE began mapping the sky, it returned an image unlike anything previously imagined, a portrait not of smooth radiation, but of rippling temperature structure. The colors used to represent the variations were exaggerated, so humans could see them visually. Blues and reds sprawled across the curve of the sky, cold pockets, warm streams, forming shapes that appeared almost biological. Nothing in cosmology prepared science for the significance of those ripples. Those ripples later became galaxies. Where background radiation was slightly warmer, density had once been greater. Gravity had been stronger. Matter condensed more easily. Across cold regions, matter thinned, stretched, and diffused. The modern cosmic web, clusters, filaments, voids, was encoded inside those faint differences. Each ripple was the seed of a world. Those fluctuations carried not heat, but destiny. A temperature imbalance became a gravitational imbalance. A gravitational imbalance became the architecture of everything that shines. The shock was profound. The universe was not a perfectly smoothing machine. It was a structure-generating system. Tiny deviations survived the expansion, and those deviations built galaxies. Yet behind the excitement of large-scale structure formation was a quieter, colder question. Something else emerged in the data. A declining trajectory. The longer scientists analyzed measurements, the clearer the trend became. The average energy of radiation was not only low, it was falling. Year after year, the wavelength of background radiation lengthened. Light that once radiated near the visible spectrum had been stretched into microwaves. Within deep cosmic timescales, even microwaves would stretch into radio frequencies, the lowest energy that electromagnetic radiation can occupy. The temperature of the universe was sliding, not exponentially, but persistently, downward. The cause was expansion. As space stretched, photons lost energy. Not by colliding with matter. Not by dissipating or absorbing into anything. They faded because the fabric through which they traveled physically enlarged. The universe grew colder not through decay, but through geometry. COBE's data forced cosmology to reconsider time not as duration, but as thinning. It suggested that cooling was accelerating, not because radiation cooled more rapidly, but because space expanded faster. The temperature drop aligned directly with increasing expansion rate. Later missions, such as WMAP and Planck, confirmed the slope. Hundreds of thousands of measurements were gathered, filtered, cross-compared, and plotted. The shape of cooling followed a consistent curve, and that curve projected forward. Cosmologists attempted to calculate what future epochs would resemble. In those models, radiation faded into mathematical limit. When the scale factor of space doubled, average background temperature halved. When it doubled again, energy halved again. The process had no reversal. The universe was not cooling toward balance, it was cooling toward emptiness. Within those projections, theoretical futures emerged. A universe without thermal gradients. A universe where heat becomes rare. A universe where each photon drifts alone. Future stars would burn their fuel, collapse, become dwarfs, become black dwarfs, become remnants. And long before matter ceased collapsing, radiation would lose coherence. Measurements from COBE revealed the beginning of this trajectory. It showed temperature decreasing not as metaphor, not as entropy metaphor, but as measurable decline. If one could freeze the universe at two different cosmic moments and compare the radiation, one would find difference. Not philosophical difference, but calculable difference. Even the coldest regions today will be warmer than the average temperature 10 trillion years from now. The deeper scientists pressed into Cobb's map, the more unsettling the implications became. The temperature variations that seeded galaxies would not remain. Gravity would eventually isolate structures. Dark energy would stretch everything apart. And at grand scale, the cosmic microwave background would fall below observable threshold. It will not disappear, but it will lengthen into wavelengths so large that no detector could ever fit enough of them to measure. Wavelengths the size of galaxies. Then larger than galaxy clusters. Then larger than the observable universe. Light becomes longer than the stage on which it travels. Cooling is not merely absence. Cooling is transformation. Even at the moment Cobb collected its field of data, the universe was already colder than the moment before. The maps represented a temperature already declining, a measurement that would never repeat. Temperature became an index of age. Scientists realized that if one measured radiation across billions of years, or across deep cosmological distances, they were effectively watching time fall through energy. The universe cooled not gradually but directionally. It possessed momentum. As cooling became quantifiable, researchers began extrapolating far futures. Calculations extended beyond fate of stars, beyond collapse of matter, into heat-death models. Heat-death was not an explosion, not a collapse, but an inability to transfer energy, because there would be nothing left to transfer it to. Temperature would approach zero. Not in human eras, not in stellar eras, but in cosmological eras, where galaxies fade like fingerprints inside fog. This recognition changed the tone of cosmology. Before Cobb, the universe was active, forming galaxies, igniting stars, merging clusters. After Cobb, the universe gained direction toward dissolution. Expansion was not opportunity, it was separation. Cooling was not stabilization, it was erasure. The shock hidden in wavelengths was twofold. First, energy variation shaped everything humanity sees. Those variations are temporary. Temporary at scale. Temporary within eternity. Galaxies formed because the radiation was uneven. Galaxies disappear because radiation will eventually become too faint to matter. Even now, each background photon is losing energy. Each second, the fabric of space expands. And though no human can perceive that cooling, it happens constantly, invisibly, permanently. One wavelength stretches while another follows. The universe lengthens itself. The faint ripples in Cobb's recorded sky map were a snapshot of a universe still warm enough to remember its beginning. Scientists studying the map did not only marvel at structure formation, they recognized loss encoded in the same measurement. The shock was not that the fluctuations existed. The shock was that they were fading. Every warm pixel becomes cold. Every cold pixel becomes colder. Every difference diminishes. The early universe held contrast. The far future holds no contrast. What will remain is uniform temperature, near absolute zero. Only in the deepest mathematical horizon will traces of warmth exist, stretched into waves so wide they no longer resemble energy. And through that recognition, cosmology came to understand its unfolding not as eternal expansion alone, but as declining energy, a universe slowly slipping into stillness. The shock hidden in the wavelengths was the realization that everything visible is temporary. Everything bright will dim. Everything structured will dissolve. Everything warm will cool. The ripples that birthed galaxies are the same ripples that will someday cease, leaving nothing but distance, silence, and the longest wavelengths ever produced by time. Across the cosmic background, temperature falls not as a single smooth curve, but as a patterned descent. After the Cobb mission revealed ripples across the microwave sky, deeper instruments were sent to tighten the picture. Satellites capable of reading temperature variations not in degrees, but in millionths of degrees. And when they measured the fading warmth of the afterglow, they revealed something unexpected. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, began that search. Launched in 2001, it traced the faint remainder of primordial fire with a sensitivity unimaginable a decade earlier. Where COBE saw blurred fluctuations, WMAP produced maps with sharp contrast, color gradients showing regions of the universe that cooled at slightly different rates. Temperature differences were tiny. Some regions were approximately 3/millionths of a degree warmer than average, others, about the same amount colder. But even such slight variations held enormous consequence. Those irregularities, if accurate, were signatures of the earliest structure formation. Matter accumulated where radiation slightly cooled. Galaxies formed where temperature dipped. But beyond those patterns, something else began to appear, something too large, too cold, and too strange. As WMAP refined its maps through successive operational cycles, the microwave background revealed an anomaly. One part of the sky, spanning an angular diameter larger than any known supercluster, was colder than theory predicted. Not slightly colder, significantly colder. This was not merely fluctuation. Models of density, matter, and primordial sound waves could not account for its magnitude. Even inflation-based estimations strained to hold it within probability. Across tens of thousands of megaparsecs, a region appeared where radiation dimmed more than expected. It became known as the cold spot. At first, its discovery was treated cautiously. Perhaps it was statistical coincidence, an improbable deviation that still fit within randomness. Perhaps observational noise distorted its edges. But when WMAP repeated the observation year after year, uncertainty faded. The cold spot was real. And then another mission prepared to measure it with greater precision. The European Space Agency's Planck satellite launched in 2009, equipped with instruments tuned specifically to map faint microwave radiation. Its sensitivity dropped uncertainty margins nearly 30-fold compared to COBE's original view. Planck was not simply a mapper. It was designed to reveal relic structures embedded within the cosmic texture itself. When Planck released its first full-sky maps, the anomaly resurfaced. The cold spot was still there. Sharper. Cleaner. Not noise. Planck measured its temperature difference relative to the surrounding background, slightly less than 70 microkelvin colder than average. By cosmic standards, such a difference, multiplied across millions of light-years, suggested something physical, not statistical, was at play. One explanation emerged. Perhaps, across that direction in the sky, there stretched an enormous cosmic void, larger than any catalogued region of underdensity. If radiation traveled through a large void, space would be less gravitationally warped along that path. The integrated Sachs-Wolf effect would stretch photons further than usual. Light would redshift more than expected. Temperature would fall, not because heat vanished, but because wavelength lengthened. It was a compelling theory. Cosmologists searched surveys of galaxy distributions and found hints of underdensity, one region of space where matter was unusually sparse. But its size did not match the observed coldness. The void did not extend far enough, nor deepen sufficiently, to account for the intensity of cooling. The hypothesis held weight, but not enough. Another interpretation arose. Perhaps the cold spot represented a statistical tale generated by inflation, an improbable but permitted fluctuation in the earliest moments. Quantum irregularities might still echo across the microwave background today, carved permanently into cosmic radiation. Yet inflation theory predicted correlated patterns. The cold spot resisted that symmetry. Planck data deepened the mystery further. Around the anomaly lay unusual temperature gradients. Patterns of surrounding fluctuations aligned in configurations that did not emerge elsewhere. The cold spot behaved not as a simple depression, but as something influenced, shaped by a process not active across the remainder of the universe. Cooling, it seemed, was not uniform. Something accelerated it. As temperature maps extended, the cooling curve appeared steeper across the cold spot path than across other directions. Radiation passing through the region faded faster than expansion alone could explain. Some cosmological papers proposed a vast supervoid large enough to distort the microwave signal, spanning perhaps billions of light-years. Others rejected that explanation, noting the void would need to exceed known structure formation timescales. Then deeper questions emerged. Why would cooling concentrate into pockets? Why would entropy, expected to move steadily toward uniformity, appear violated? Cold, in that context, no longer aligned with randomness. It hinted at structure. The cold spot may not mark emptiness, some argued, but presence of something unseen. Speculative models offered possibilities. A collapsing curvature well, a remnant of early phase topology. Parallel cosmic inflation domains leaving imprint through boundary contact. A defect left during symmetry breaking in the young universe. None achieved agreement. None dissolved the anomaly. The cold spot remained, a quiet region in the cosmic afterglow where radiation thinned, where the afterfire dimmed more sharply than the rest of the universe. And as data accumulated, a deeper realization emerged. Cooling was not simply passive decay. Expansion alone did not govern it. Patterns within the microwave background suggested thermal descent occurred more rapidly in certain directional volumes, accelerating past theoretical gradients. Where matter thinned, radiation fell faster. Where primordial density dipped, the temperature slope steepened. The universe seemed to cool unevenly. Across large patches of sky, the fading warmth aligned with known structure formation. Denser regions slowed cooling, underdense regions sped it. But the cold spot accelerated beyond prediction. There was no agreement on cause. But the shape of the anomaly revealed something profound. Cosmic cooling was influenced, not as a uniform cosmic trend, but as a patterned field, shaped by ancient imprints of early physics. What the universe cooled toward remained clear. Silence. Isolation. An energetic zero asymptotically approached. But what it cooled through remained uneven. That unevenness was not noise. It was information. Encoded into faint radiation, stretched across a trillion kilometers, lay memory of primordial turbulence, structures that appeared before galaxies existed, before matter condensed, before even laws of thermodynamics fully settled. Cooling, in that narrative, was not merely the exhaustion of heat. It was the unfolding of origin. Temperature did not simply drop. It revealed where the universe bent differently at its beginning. It revealed where energy froze into variations that no later process ever erased. The cold spot marked one of those places, one of the final, untouched scars of cosmic birth. Its existence shifts the nature of cosmic cooling from passive dissipation to active structure. The universe is not cooling everywhere at the same pace because it did not begin everywhere with the same balance. Where matter accumulated, temperature slowed. Where matter thinned, background cooling raced ahead. And in the cold spot, something acted stronger than either. It is still unknown whether a void, a relic curvature, or something older carved that hollow in the microwave light. But its presence offers an unsettling truth. The future will not cool uniformly. Different regions will fade at different rates. Radiation will vanish directionally. Heat will fall piecewise, not all at once, but by cosmic location. And the cold spot will fade first. In a universe that stretches toward absolute stillness, that region will reach it sooner, its warmth dissolving, its photons lengthening, its past disappearing into wavelengths too large to measure. Cooling is not passive. Cooling has shape. Cooling has regions. Cooling remembers origins. And where that memory deepens most, cold becomes strange. Near the end of the 20th century, cosmologists believed the universe was slowing down. Gravity, spread across every cluster, every filament, every massive body, was expected to pull back against the expansion first observed by Hubble. Galaxies, spread across cosmic distances, were thought to be climbing upward against an invisible slope. And in time, that slope would level, flatten, or reverse. The future seemed predictable. Expansion would weaken, then stall. Cold would deepen, but slowly. Everything changed in 1998. The discovery began not with cold instruments in orbit or data from microwave maps, but with dim explosions at the edge of visibility, Type Ia supernovae, stellar deaths bright enough to serve as cosmic measuring candles. Their luminosities, uniform in their physical nature, allowed astronomers to compare brightness against distance. Through them, cosmic motion could be traced with precision. Two observational groups led that effort, one centered at Lawrence Berkeley National Laboratory, Another spread across institutions in Australia and Chile. Among those guiding the measurements were Saul Perlmutter, Brian Schmidt, and Adam Rees, three scientists who brought the sky to its most unsettling revelation. Supernovae that should have been bright appeared dimmer. And dimmer did not mean distant in ordinary terms. Dimmer meant farther than models predicted. The universe was not slowing. It was accelerating. Galaxies were drifting away faster now than they had billions of years earlier. The expansion curve was not flattening. It steepened. Space was not relaxing. It was stretching with increasing urgency. To explain this, cosmology introduced something new, not matter, not radiation, not curvature. Dark energy. A name chosen not because it was known, but precisely because nothing about it was. It was not dust drifting between galaxies. It was not hidden stars or diffuse gas. It was not force carried by particles that could be trapped, counted, or observed. Dark energy was not energy in any classical sense. It was something built into space-time itself. Einstein's general relativity had once contained a term, the cosmological constant, inserted to stabilize a static universe. Later, when expansion was discovered, the term was removed. Now cosmology restored it, not as artifact but as consequence. Acceleration requires repulsion, and repulsion requires a field. Dark energy became that field. Its behavior was counterintuitive. Instead of diluting as space expanded, dark energy remained constant. Density stayed fixed. Volume increased. The amount of dark energy increased with every pulse of expansion. What this meant was profound. Every future moment would stretch space more than the moment before it. Cold, therefore, would not fall steadily, it would accelerate. The discovery fundamentally changed cosmic destiny. Before 1998, models predicted either slowing expansion or collapse. After 1998, collapse vanished from probability. The universe would never return to its denser past. Matter density began declining faster than expected. Galaxies spread apart beyond gravitational influence. Stars born today would shine into emptiness more extreme than anything preceding human thought. Radiation density fell faster than the cooling predicted by cosmic microwave decay alone. Stretching wavelengths no longer slowed, they rushed. Thermal history shifted from gradual fading into exponential descent. A new cosmic trajectory appeared. Expansion accelerates. Distance increases. Light redshifts. Heat thins. Dark accelerates further. A feedback loop embedded in spacetime. The Nobel Committee recognized its significance in 2011, awarding Perlmutter, Schmidt, and Rees for uncovering the accelerating universe. Their discovery did not simply reveal motion. It revealed fate. Cold would not settle gradually. It would deepen toward uniformity at a pace that outruns structure. Galaxies no longer drift passively, they separate into isolation. Gravity weakens not because its strength changes, but because its reach becomes finite against expansion that does not halt. Eventually, every cluster outside the local group passes an unreachable horizon. Light it emits stretches beyond measurable thresholds. That light loses energy, not through absorption, not through scattering, but through time. Dark energy ensures that process cannot reverse. Cooling becomes irreversible. Heat cannot return because no compression will occur. Space will never shrink. Matter will never collapse again into universal density. There will be no large-scale reheating. Entropy continues, but isolation accelerates its path. At distances exceeding tens of billions of light-years, galaxies already vanish behind cosmological horizons. Their radiation lengthens into invisibility. Each photon becomes colder than background levels predicted before acceleration was discovered. The universe does not freeze at once. It freezes region by region, horizon by horizon, as separation increases. The cosmic background approaches zero temperature not as simple straight decline, but as curves steepening into asymptotic silence. Late-time models estimate a background temperature approaching 1/10 of a Kelvin in tens of trillions of years. Later still millikelvin. Later, microkelvin. Eventually, a value indistinguishable from zero. Not because heat reaches zero absolutely, but because heat becomes unmeasurable. Dark energy ensures that cold arrives not uniformly in detail, but uniformly in outcome. The distribution of matter today, clustered, filamentary, rich in structure, will dissolve into thermal sameness. Distances increase until meaningful connection ceases. Energy loses capacity to travel. Light cannot cross space that expands faster than its movement. Thermal influence no longer spreads. Dark energy makes heat irrelevant. And in that far cosmic future, something striking happens. Temperature not only falls, but equalizes. Variations that once seeded galaxies, that once shaped clusters, that once traced primordial fluctuations, flatten. Cold becomes equal everywhere. There will be no new sources of imbalance. No new stars form from collapsing clouds once hydrogen depletion reaches final states. No supernovae radiate across voids so vast that radiation cannot penetrate them. No galaxies collide and merge. Interactions decline, slow, and cease. Thermal gradients dissolve. The universe enters asymptotic equilibrium, not because equilibrium is reached, but because interaction stops. When dark energy was discovered, cosmology stepped into that distant forecast. Cold was no longer passive consequence of expansion. It became mathematical destiny. Not linear descent. Not diminishing slope. Exponential collapse of remaining heat. And in that future, the cold becomes more than environmental. It becomes structural. The universe does not merely cool. The universe becomes defined by cold. Dark energy ensures that outcome. The cosmic background's fading temperature is no longer a trace of ancient fire. It becomes a boundary, a point beyond which no new energy can cross. Cold predicted to spread everywhere. Cold predicted to equalize. Cold predicted to last forever. From 3 faint supernovae measurements came this entire view. From dim explosions at cosmic edges came the forecast of final time. The universe expands faster. Heat thins faster. Light stretches further. Gravity loses reach. And dark energy writes the final sentence. Everything grows colder not slowly, but acceleratingly, until what remains is silence that cannot reverse. In the known universe, life has always existed in the gaps between extremes. It thrives where heat meets cold, where energy flows from high to low, where gradients, however fragile, allow chemistry to move forward. Biology is not built from warmth alone, but from the difference between temperatures. Life consumes imbalance, rearranging matter one reaction at a time. And in this cosmic story, temperature is destiny. For billions of years, that destiny has been shaped by stars. Stars are the engines of usable energy. Every heartbeat of cellular chemistry on Earth has its origin in stellar fusion, hydrogen forced into helium by heat that cannot be imagined on terrestrial scales. From that thermal violence, photons travel across planetary distances, eventually becoming sunlight, warmth, and motion. Life learned to exist by capturing those flows. But in a universe moving toward equilibrium, the flow weakens. Cosmology predicts that the deep future belongs not to heat, but to its absence. The cosmos expands, and with expansion comes dilution. Radiation spreads thinner. Background temperatures fall. And step by step, gradients collapse. This decline is not sudden. It unfolds across unimaginable spans. Trillions of years into the future, galaxies stop forming new stars. Their raw hydrogen reserves shrink. Stellar birth ceases. What remains are the remnants, fading embers of what once were living suns. They become white dwarfs, dense, exhausted stars no longer burning anything, merely cooling. For eons they glow with residual heat, slowly shedding the last memory of fusion. Their light dimming, their surface hardening, their cores crystallizing. Beneath that fading glow, carbon atoms arrange into a lattice so dense that astronomers describe it as a cosmic diamond, floating in silent dark. Eventually, even that light will end. The universe then enters what physicists call the degenerate era. It is named not for decay, but for structure. The matter that survives is degenerate matter, supported not by heat, but by quantum pressure alone. In that age, temperature becomes a relic. White dwarfs cool until their radiation becomes indistinguishable from the emptiness around them. What were once blue-hot stars become cold spheres of crystal carbon and iron-dark rock frozen at near absolute zero. Black dwarfs, objects theorized but not yet existing, will fill what used to be starfields. Around them, planets drift. Their orbits no longer warmed by parent stars. Their surfaces glaze in sheets of frozen water, frozen gases, frozen oceans. Atmospheres collapse. Geology halts. Magnetic fields fade. Their internal heat, once the memory of formation, dissipates. There is no place left where life could sit between warm and cold, because everything is the same temperature. The biological definition of death begins here. Not simply the end of organisms, but the end of possibility. All known life depends on gradient. Metabolism is imbalance. Heat absorbed, energy released, electrons moved from high state to low. Without gradients, chemistry becomes still. The universe cools toward equilibrium, and equilibrium is motionlessness. Stars that once carved structure into space dissolve into anonymity. Their light no longer travels, because there is no heat left to lose. Space itself is too cold to contrast against anything. Galaxies remain, but dimly, no spirals glowing, no bands of blue young stars. Only dark hulls of matter orbiting a silence that cannot be broken. Their black holes persist, slowly evaporating over unimaginable spans through Hawking radiation, until even they become faint whispers of energy returning to nothing. In this cooling cosmos, time does not stop, but meaning becomes thin. Temperature once arranged the cosmos like music, high and low, contrast and direction, pressure and release. Now the melody ends. Inside planets, biological archives freeze. Molecules that once carried memory, DNA, amino acids, sequences of self, become silent. Their patterns remain but without motion, without metabolism, without replication. Complexity falls asleep. Thermodynamics has always been the most patient storyteller. In its laws, biology is simply a brief interruption. Life arises when gradients are steep. It organizes matter to slow the return to uniformity. It feeds on difference. But entropy is the inheritance of everything. Across cosmic scales, entropy is not destruction, it is smoothing. It is the fading of contrast, the cooling of imbalance, the quiet sealing of processes that once defined existence. Eventually, every remnant star cools into uniform cold. Every planet becomes indistinguishable from the dust around it. The cosmic microwave background, already approaching just above absolute zero, continues its decline. Photons stretch until their energy approaches nothing. Stillness spreads. In that vast darkness, the universe stops producing new gradients. No heat sources remain to ignite change. All that remains is black matter, dense, silent, unlit, moving only because motion is difficult to erase. Time stretches, but nothing happens inside it. The biological story ends, not in fire, but in temperature death. The cosmos enters a silence deeper than vacuum. A silence that is not the absence of sound, but the absence of anything that could break it. What remains is equilibrium, perfect and irreversible. Life, as currently understood, depends on heat flowing from somewhere to somewhere else. Once the flow stops, biology is unmade. The universe becomes a single temperature, flat, neutral, unchanging. Galaxies fade into invisibility. Stars are no longer being born. Planets drift in shadows without sources. And in that final age, the universe remembers its bright beginning only as structure, cold remnants that once glowed, now crystallized into quiet matter. Temperature once seeded life. Temperature now erases its stage. This is the long night of the universe. A night with no dawn, where the last heat dissolves, and existence cools into stillness. In the vastness of space, sound is impossible. There are no molecules close enough to collide, no medium dense enough to carry waves. The cosmos is a vacuum, a realm where the familiar echo of voice or wind cannot exist. Yet silence in the universe is not simply the absence of sound. It is not emptiness in the human sense. Silence has a measure. Silence has a shape. Silence carries its own temperature. For billions of years, the universe has hummed. Not in vibrations audible to ears, but in the subtle, persistent chatter of photons, the low murmur of cosmic microwave background radiation, the faint warmth left over from the birth of everything. Every photon is a message from the past, a tiny carrier of energy and information drifting across billions of light years. The universe, in this sense, is never truly quiet. Even in the void, space speaks. But cooling changes that hum. As expansion stretches space, photons are redshifted, pulled into longer wavelengths, their energy diminished. Their frequencies drop, their signals fade. The whisper of the cosmos grows quieter with every passing eon. Regions once alive with subtle thermal fluctuations begin to flatten, and the information encoded in those photons, traces of the early universe, of density ripples, of nascent galaxies, begins to vanish into imperceptibility. Cooling, in this sense, is not merely the loss of heat, but the erosion of memory itself. As the universe expands faster, driven by dark energy, causal horizons emerge. There are regions of space that are moving away faster than light can traverse. Photons emitted from distant galaxies today will never reach certain observers tomorrow. Space itself stretches beyond communication. What was once connected becomes forever isolated. Information, in the cosmic sense, is lost. The universe forgets. What silence hides is not emptiness but the disappearance of traces, the thermal footprints of a history that can no longer be accessed. Cosmologists call this horizon the ultimate limit of causality. Within it, events can influence each other. Beyond it, events vanish from possibility. As cooling accelerates and horizons grow, more regions of the universe slip beyond the grasp of light and energy. The temperature of silence is the temperature of irretrievable information, the fading signal of reality itself. The hum of photons slows, stretches, diminishes, until even the background radiation becomes almost unmeasurable. Where there was once contrast, there is uniformity. Where there was once energy flow, there is stillness. This is the universe at its most reflective. Silence is no longer just absence. It is the thermodynamic consequence of entropy. The fading of temperature corresponds to the fading of knowledge. Each cooled photon is a story unread, a moment unrecoverable. Galaxies drift beyond horizons, stars fade into black dwarfs, and light that once carried structural memory is stretched thin into virtual non-existence. Heat is not only energy, it is information. As the universe grows colder, the loss of energy mirrors the loss of understanding, the evaporation of causal connection. In the final, deep future cosmos, silence is absolute not because nothing happens, but because nothing can ever again be known. In that sense, silence has a temperature. It is the cold of lost photons, of redshifted whispers, of horizons expanding faster than any signal can travel. It is the cold of a universe remembering less and less, until the cosmic hum becomes a whisper beyond comprehension, until all gradients vanish and all memory decays. Cooling is thus also forgetting, and silence is the thermodynamic signature of that forgetting. The universe, once speaking, will one day become a quiet archive whose pages are unreadable. Temperature is not merely a measure of kinetic motion, it is the medium through which memory survives. And as the last photons fade into long wavelength invisibility, silence, measurable, cold, and absolute, will prevail. In the end, the temperature of the universe is the temperature of forgetting, and the deeper it cools, the more the universe forgets its own story. The universe, as modern physics teaches, is bound by the unyielding arrow of entropy. From the first moment of the Big Bang, disorder has marched relentlessly forward. Stars burn, particles scatter, galaxies collide. Every process a small step in the universal tally of chaos. Thermodynamics insists that disorder increases, that gradients of energy smooth out, that the cosmos tends toward randomness. This principle underpins our understanding of reality, shaping predictions from the collapse of stars to the formation of black holes. Yet, as the universe cools under the influence of expansion and dark energy, a strange anomaly emerges. Observations of the cosmic microwave background, refined by missions like WMAP and Planck, reveal that the average temperature is not simply decreasing, it is approaching a nearly absolute uniformity. The difference between one region of space and another diminishes. Fluctuations flatten. Variation fades. The cosmos, in its deep future, is not chaotic. It is unervingly ordered. This is the heat-death paradox. Entropy predicts disorder, yet the ultimate state appears to contradict it. In a universe where cold spreads relentlessly and light loses energy to expansion, uniformity prevails. Disorder, it seems, has no place. Instead of a tumult of decaying stars and fluctuating energy, the cosmos slides into homogeneity, a smooth, silent, and predictable expanse. Roger Penrose, one of the most profound thinkers in cosmology, has framed this puzzle through the lens of gravitational entropy. Unlike conventional thermodynamic systems, where heat defines entropy, gravity behaves differently. Mass concentrations, stars, galaxies, black holes, store entropy in their structure. A black hole, the ultimate gravitational object, is paradoxically an island of enormous disorder within the smooth fabric of space. Its surface area, not volume, measures its entropy. When black holes evaporate over unimaginable timescales via Hawking radiation, this concentrated disorder disperses, releasing energy into an ever-cooling cosmos. Yet the deeper mystery remains. The uniform cold of intergalactic space does not reverse. It does not increase in disorder as black hole entropy dissipates. Instead, the universe approaches a final state of serene homogeneity, in which matter is sparse, radiation is weak, and energy gradients vanish. Chaos has been diffused, and yet cold, structured, and stable order remains. In this context, the universe is ending not in disorder, but in order. Entropy, the classical measure of chaos, seems to have been sidestepped. The laws of thermodynamics, so reliable in closed systems, are challenged by the cosmic scale and the accelerating expansion. If the final state is uniform, if heat becomes negligible, and if no gradients remain to drive change, then entropy as we understand it is no longer a guide to the cosmos. This is more than a theoretical quirk. It is a profound threat to the assumptions underlying physics. Heat death, long thought to be the triumph of disorder, instead appears as the triumph of symmetry. The universe ends in near-perfect uniformity, a deep freeze where all motion, all fluctuation, all difference has vanished. The arrow of time, intimately tied to entropy, persists, but it points into an ever-expanding, ever-cooling void where the distinction between past and future blurs. Black holes, once the ultimate repositories of disorder, will have evaporated completely, leaving behind only cold photons and dark matter, dispersed beyond interaction. The universe's memory, the record of formation, collision, life, and energy, remains encoded in a faint residual background, but its capacity to influence future events ceases. The cosmological horizon, imposed by accelerating expansion, isolates every region of space, rendering energy gradients and causal interactions finite and inaccessible. Thus emerges the paradoxical reality. The universe, governed by entropy, seems poised to end in order. Gravitational disorder, encoded in black holes, disperses, yet the vast expanses between vanish into near-perfect equilibrium. Classical thermodynamics, which has guided our understanding of heat, energy, and disorder for centuries, encounters a limit at the scale of the cosmos itself. The rules that govern engines, chemical reactions, and planetary climates falter when applied to an accelerating, cooling universe where dark energy dictates the tempo. In this emerging vision, the future is not chaotic. It is silent, cold, and uniform. The classical arrow of entropy points forward, but the destination, uniform temperature, no gradients, minimal energy, suggests a subtle triumph of order. Time marches on, yet its significance dwindles as events fade into uniformity. The universe, in all its immensity, becomes a single temperature, a single state, a single quiet. The heat-death paradox is not merely a scientific curiosity, it is a philosophical confrontation. It forces a reconsideration of what it means for a system to evolve, to decay, to die. The final state of the cosmos, as suggested by accelerated expansion and dark energy, may defy the intuitive logic of disorder. In this deep future, the universe exists in a silent symmetry that challenges the very foundation of thermodynamic expectation. Order, not chaos, prevails. Cold, not disorder, defines the ultimate cosmos. The universe, once wild with energy and structure, ends in a quiet so precise that it seems almost unnatural. All that remains is the measure of absence, the temperature of uniformity, the eerie consistency of a cosmos that has cooled beyond fluctuation. In this end, physics confronts its own limits, and the universe whispers a final paradox, that even in the domain of entropy, order may triumph. In the far, unfathomable reaches of cosmic time, the universe will arrive at a stage few can truly imagine. Trillions of years from now, the stars that once punctuated the night sky with their fiery brilliance will have ceased to exist. Galaxies, emptied of young stars, will drift like ghostly hulls through an ever-expanding void. The familiar sources of light and heat will vanish, leaving a cosmos bereft of its once vibrant glow. This is the beginning of the starless era, a time when nuclear fusion, the engine that fueled life, shaped planets, and illuminated the cosmos, has long ceased. Hydrogen, the raw fuel of stars, is depleted. Stellar nurseries have gone cold, and the last blue giants have burnt themselves out, collapsing into faint white dwarfs, neutron stars, or black holes. These remnants, dense and silent, become the final landmarks of a universe whose brilliance is fading into shadow. For eons, black holes, the most extreme survivors, will dominate. They are the last engines of concentrated energy and entropy, swallowing matter, warping space-time, and storing the accumulated disorder of billions of years. Yet even they are not eternal. Through the subtle, relentless process of Hawking radiation, black holes lose mass. The largest, most massive black holes will evaporate only after 10 to the power of 100 years, releasing their entropy back into a cosmos already deep into the cold. When the final Hawking radiation dissipates, the universe enters a state unlike any previously known. There are no stars to shine, no black holes to anchor matter, no sources of usable energy remaining. The universe is populated only by diffuse particles, protons, electrons, neutrinos, photons stretched to invisibility by cosmological expansion. These particles drift alone, unbound, unable to interact in meaningful ways. Each exists in isolation, separated by distances so vast that even light, moving at its finite speed, cannot bridge the emptiness. This is cosmic isolation. It is not merely cold, for temperature is a measure of energy. Even the faint residual heat from evaporating black holes or relic photons has largely dissipated. The universe's freezing is not driven by the absence of energy alone, but by the increasing separation of everything that once could interact. Space itself expands relentlessly, stretching distances to scales beyond causal reach. What was once connected, the remnants of galaxies, the scattered particles of former stars, becomes unreachable. They are islands in a vast, silent ocean of vacuum. In this era, entropy is no longer about the chaotic rearrangement of matter. Disorder has already been diffused. The universe is uniform, empty, and isolated. Gradients vanish because interactions vanish. Thermodynamic evolution halts not from lack of energy alone, but because nothing can meet anything else to transfer it. The concept of locality, the notion that cause and effect operate through space, is broken on cosmic scales. Every particle is frozen in relational solitude, drifting eternally without influence or being influenced. Distances define existence now. The void is no longer a background. It is the primary architect of the cosmos. Matter survives, but it is irrelevant. Energy remains, but it cannot flow. Light exists, but it cannot travel far enough to illuminate a neighbor. The universe does not freeze because it is cold in the sense humans understand. It freezes because the vast expansion has made connection impossible. Space becomes a prison of separation, a realm where the architecture of interaction collapses. Philosophically, this is profound. The universe, once vibrant with structure, with galaxies, stars, planets, and life, now becomes a collection of isolated remnants, each alone in an unbridgeable expanse. Memory, encoded in matter and radiation, is dispersed and unreachable. Knowledge, as we conceive it, cannot propagate. Time continues, but it is a sequence of isolation, a chronicle of disconnected points adrift in an infinite ocean. Distances stretch beyond the reach of even light, and with that, the causal web that once bound events together unravels. Particles may collide occasionally by random chance, but such events are vanishingly rare, irrelevant to the global scale of the cosmos. Structures are ephemeral. Gravity, though ever-present, cannot pull objects together over distances that grow faster than interaction allows. The universe's expansion, powered by dark energy, ensures that each region remains forever beyond influence. This is a universe in which the concept of community has vanished. Not just for life, which long ago vanished with the cooling of stars and the cessation of gradients, but for all matter. Every particle is an island, every photon a solitary traveler lost in infinite space. The end state is not destruction, it is isolation. Not collapse, but the ultimate separation. The cosmic map becomes a constellation of loners, drifting eternally in a frozen void. Even black holes, once the repositories of immense gravitational pull and localized energy, have dissipated. Their Hawking radiation, emitted over unimaginable timescales, spreads thin and is stretched into irrelevance by expansion. Once concentrated entropy disperses into the emptiness, but without interaction, it cannot produce change. The universe becomes an eternal ledger of what was, but with no capacity for further action. In this sense, the universe does not simply die from cold, it dies from distance. The fundamental connective tissue of causality has unraveled. The fabric of reality, once alive with interaction, now exists as dispersed, unreachable points. The cosmos has achieved an extreme of isolation, a form of stasis dictated not merely by thermodynamics, but by geometry and expansion. The era after black holes is thus a realm of ultimate solitude. It is a testament to the power of expansion and the subtle tyranny of time. All that remains are particles, radiation, and dark matter, separated by distances beyond comprehension. The universe has not ended in fire, or turbulence, or chaotic collapse. It has ended in quiet separation, a cold where interaction is impossible, a silence defined not by the absence of sound, but by the impossibility of connection. Here, at last, the universe becomes a mirror to the limits of comprehension. Time persists, yet it is unobserved. Space stretches, yet nothing perceives it. Matter exists, yet it is irrelevant. The cosmos is frozen not in energy alone, but in the gulf between all that survives. In this era, isolation becomes the defining law of existence, the final stage of a universe whose expansion has made everything forever unreachable. The era after black holes is the ultimate testament to cosmic solitude. It is a universe in which silence is complete, not merely the absence of vibration, but the absence of relational meaning. Distance dictates fate, and the end of all things is measured in separation, not in decay. The cosmos, once teeming with connection, has stretched itself into an infinite tapestry of islands, a quiet more profound than any human imagination can encompass. And in that quiet, the universe, vast beyond measure, drifts alone. In the vast, expanding expanse of the universe, light itself succumbs to the passage of time. Photons, the messengers of electromagnetic energy, once vibrant and swift, lose their vitality as space stretches around them. The universe is not static, it grows ever wider, and as it does, the wavelengths of light are pulled taut, elongated beyond recognition. A photon that began its journey in the energetic glow of a young star now drifts silently, its oscillations slowed, its frequency diminished. In the near future of cosmological time, these photons will have decayed to extraordinary lengths. From nanometers to meters, from kilometers to planetary scales, their wavelengths stretch into realms that boggle the imagination. The cosmic microwave background, once a faint whisper of the Big Bang, will have cooled so dramatically that its photons ripple across distances larger than entire star systems. The energy they carry approaches insignificance, fading into the background of an ever-diluting universe. Mathematically, this process is understood through the cosmological redshift. As the scale of space expands, the wavelength of each photon stretches in proportion. Energy, inversely proportional to wavelength, decreases. The formula E equals h nu, where h is Planck's constant and nu the frequency, captures this diminishing vitality. As nu approaches zero, the energy vanishes into near invisibility. Even the faintest whisper of radiation, the last vestiges of the universe's heat, loses significance. The cosmos becomes a realm where light exists, but only as an echo of its former self, oscillating at frequencies so low that the passage of millennia is required for a single wave to complete a cycle. In this stage, cold is no longer merely felt. It is a concept measured by mathematics. Thermometers, even hypothetically scaled to cosmic dimensions, could not register such faint energy. The universe has entered a domain where temperature is defined not by experience but by theoretical prediction, where energy is so sparse that it approaches zero, yet the laws of physics can still describe its decay. Cosmologists can calculate the final wavelengths, the ultimate frequencies, yet they are no longer tangible, they are beyond interaction, beyond influence. These planetary-scale waves, later expanding to cosmic dimensions, represent a universe in profound stillness. They are the smallest frequencies ever predicted, the ultimate attenuation of light, and the final sign that the universe has cooled beyond fluctuation. Heat death is no longer a metaphor. It is encoded in the oscillations of these ancient photons, stretched to the limits of space itself. The story of the universe's cooling is told not only in the absence of stars or the fading of black holes, but in the decay of light itself. Even photons, the fastest messengers, are powerless against the relentless stretching of space. Energy becomes negligible, and the cosmos enters a state in which change is nearly impossible. Only through the language of mathematics, through the careful calculations of frequency, wavelength, and energy, can scientists measure the final murmurs of a dying universe. In this realm, temperature has a new meaning. It is no longer warmth or cold in the human sense. It is a measure of potential, a metric for the remaining capacity for interaction, a testament to the energy that once flowed freely and now is nearly extinguished. The smallest frequencies remind us that even the fundamental quanta of light are subject to the inexorable expansion and cooling of the cosmos. These cosmic waves, immense and slow, ripple through an otherwise silent void. Their passage is imperceptible to any observer, for no observer remains. Yet in their stretching, they encode the story of a universe that began with unimaginable heat and light and now drifts toward an energy so sparse that its presence is detectable only through calculation, only through theory. The mathematics of their decay highlights the intimate link between space, time, and energy. As the universe expands, the relationship between distance and wavelength dictates the fading of photons. This is not a gentle dimming. It is an inexorable attenuation to near zero. The energy contained in these waves, once sufficient to ignite atoms and catalyze chemical reactions, now teeters on the edge of nothingness. Ultimately, the smallest frequencies ever predicted are a testament to the universe's ultimate quiet. They signify the final stage of cosmic evolution, the endpoint of thermodynamic decay, and the deepening of silence into measurable, calculable stillness. In these infinitely stretched oscillations, we witness the closing of a story that began in fire and light and ends in near absolute uniformity and extreme cold. The universe, in this final act, does not explode or collapse. It does not twist violently or vanish in catastrophe. It cools, stretches, and quiets, leaving behind these ancient photons as the last measurable trace of energy. Their wavelengths, kilometers long, eventually planetary, and finally cosmic in scale, encapsulate the ultimate fate of light, heat, and energy itself. Cold becomes a measurable abstraction, a numerical value in equations that describe a cosmos that has long ceased to teem with activity. The smallest frequencies ever predicted are the universe's final whisper. In their slow oscillations, they mark the boundaries of what was once dynamic and radiant. They encode the irreversible stretching of space, the fading of energy, and the approach of a universe where nothing new can happen. In these wavering, elongated signals, the story of everything, the rise of stars, the dance of galaxies, the emergence of life, is distilled into a silent, frozen trace. And so, as the universe stretches into eternity, the photons continue their languid journey. Their energy, approaching zero, is the ultimate measure of cold, the final reflection of a cosmos that has cooled beyond fluctuation, beyond heat, and beyond meaningful interaction. In this era, cold is not just absence of heat. It is the measurable trace of the smallest frequencies ever predicted, the final testament to the universe's inexorable drift towards stillness, silence, and uniformity. As the universe drifts into the final stages of its thermal decline, cosmologists gaze at the horizon of possibility and confront questions that blur the boundary between observation and speculation. The cooling of the cosmos, gradual for billions of years, may not merely coast toward uniformity. It could accelerate, propelled by forces so subtle and profound that their effects ripple through space and time, reshaping the ultimate fate of everything. Two leading frameworks have emerged in theoretical physics, each painting a future colder, stranger, and more radical than the silent drift toward heat death: phantom energy and false vacuum collapse. Phantom energy is a specter of the cosmos, a hypothetical form of dark energy that exceeds all expectations. Unlike the cosmological constant that governs the current acceleration of expansion, phantom energy grows stronger as the universe expands. Its density increases with time, a perverse inversion of conventional intuition, where energy is not diluted by volume but amplified. The implications are profound. Expansion does not merely stretch space, it begins to tear it apart. Galaxies drift beyond each other at unimaginable rates, stars lose causal contact, and atoms themselves are pulled thin as space-time fractures on the largest scales. In this scenario, cooling is not a gentle decline. It becomes a runaway process. Radiation is redshifted to lengths far beyond comprehension, energy dissipates faster than the slow stretching of ordinary expansion would predict, and temperatures approach a theoretical dark zero, a state where energy is not merely scarce but fundamentally inaccessible. The mathematics underpinning phantom energy are hauntingly elegant. The Friedmann equations, central to cosmology, accommodate an equation of state parameter less than -1, a condition that accelerates expansion toward infinity in finite time. Cosmologists term this the Big Rip, an ultimate tearing of the cosmic fabric. In the context of cooling, it is a universe in which temperature is not only declining, it is violently extinguished. Photons, matter, and even space-time itself succumb to the inexorable pull of an expanding void, leaving a cosmos colder than silence, colder than anything we can imagine from the physics of our current epoch. Yet the universe offers another, even stranger possibility: false vacuum collapse. Here, the story moves from the cosmic to the quantum. The vacuum of space is not empty but filled with a scalar field, a subtle energy that permeates all of existence. Current observations suggest this field is metastable, a false vacuum, slightly higher in energy than a true, lower state. Should quantum fluctuations trigger a transition to this true vacuum, the consequences would be catastrophic and absolute. Space itself would rewrite its rules. Physical constants could change, the structure of matter might be destroyed, and the very laws governing temperature, light, and energy could be reset. In a false vacuum collapse, cooling is not merely accelerated, it is violently redefined. The universe does not slowly drift toward lower temperatures. Instead, the scalar field drops, energy landscapes shift, and the cosmic fabric undergoes a fundamental realignment. Existing photons and particles could be obliterated or transformed. Heat as we understand it could vanish or be redistributed in ways that erase all memory of prior energy states. Temperature, the measure of motion and interaction, becomes meaningless in a universe that has rewritten its own physical laws. In this model, ultimate cooling is not a passive decline but a radical reset, an annihilation of the familiar cosmos in favor of a new vacuum whose properties are unknowable. Both phantom energy and false vacuum collapse confront a chilling truth. The universe's approach to ultimate cold may be far more dramatic than gradual decline. Phantom energy envisions an accelerating, tearing universe where temperature drops toward theoretical zero. False vacuum collapse envisions a cosmic reset, a redefinition of existence in which previous energy states, and the concept of temperature itself, may cease to exist. These ideas stretch the imagination, yet they emerge from the equations of general relativity, quantum field theory, and cosmology. They are not flights of fancy but rigorous extrapolations of known physics into the extremes of possibility. The implications extend beyond pure theory. Phantom energy suggests a universe where all structure, from galaxies to atoms, is ultimately undone. Cooling is no longer a gentle fade but a violent erasure, a universe unrecognizable in its final stages. False vacuum collapse, in contrast, implies a discontinuous jump, a sudden, catastrophic transition where temperature, energy, and even matter may be fundamentally altered. In both cases, the end of cosmic thermal history is not a slow dimming but an existential event, a final statement that the universe may be governed by processes as strange as they are inevitable. Scientists approach these ideas with caution. Observations of supernovae, the cosmic microwave background, and large-scale structure constrain the possible behavior of dark energy, yet uncertainty remains. Quantum fluctuations, by their nature, defy deterministic prediction, leaving false vacuum scenarios as probabilities rather than certainties. Yet the very act of considering these models illuminates the profound fragility of the cosmos. The universe's cooling is no longer a simple function of expansion. It is entangled with the deepest mysteries of energy, vacuum, and the fundamental structure of reality. The philosophical resonance is equally profound. Phantom energy and false vacuum collapse confront humanity with a cosmos in which the decline of heat and energy is not merely inevitable but potentially violent, a universe that may rip apart or reset itself entirely. The cold of space, once a gentle drift toward stillness, becomes a canvas for extremes, an ultimate stage where order, disorder, light, and motion are subject to forces beyond comprehension. The temperature of silence, the fading energy of cosmic photons, the eventual dissipation of stars and black holes, all are now seen through the lens of possible acceleration, of a cosmos racing toward extremes we can scarcely imagine. Ultimately, the theories of ultimate cooling acceleration remind us of our place in an uncaring, immense universe. Whether through the inexorable pull of phantom energy or the abrupt rewriting of space-time in a false vacuum collapse, the cosmos is not simply fading, it may be racing, restructuring, or even annihilating its former self. The slow, poetic decline measured by the cooling of the cosmic microwave background could be only the prelude to events that surpass human intuition. The universe's silence, its near-zero temperatures, and its stretched photons are all part of a larger story, a narrative of potential extremes where the end is not simply cold but extraordinary in its magnitude. In these final possibilities, the very nature of temperature, light, and existence is questioned. The universe, once a theater of warmth and motion, may end in a spectacle of accelerating cold or a sudden, incomprehensible reset. Phantom energy and false vacuum collapse are more than theories. They are glimpses into the ultimate fate of all things, a reminder that the universe's quiet march toward lower temperatures may conceal forces and transformations as strange as the cosmos itself. In contemplating these models, humanity touches the edge of understanding, peering into a future where cold is not merely absence of heat but the herald of cosmic transformation, a temperature so extreme and so absolute that it challenges the very foundations of physics, time, and memory. As the universe drifts toward ever lower temperatures, the question emerges: is this decline a gentle, inevitable descent, or the result of hidden, accelerating forces? To answer this, scientists have turned to the most sophisticated instruments ever conceived, a suite of observatories and experiments designed to detect the subtle mechanics behind cosmic cooling. Each tool peels back layers of the universe's quiet decline, probing the behavior of light, matter, and energy across vast spans of space and time, seeking evidence that the cosmos itself is whispering the secrets of its fading heat. At the forefront is the James Webb Space Telescope, humanity's most powerful eye into the distant past. Its infrared instruments are tuned to capture photons emitted billions of years ago, photons that have traveled across expanding space, stretching, cooling, losing energy as they traverse the universe. By observing these ancient travelers, Webb can detect minute variations in redshift over time, the so-called redshift drift, a phenomenon predicted by general relativity. If the universe's cooling is purely passive, these measurements will align with established models of expansion and cosmic microwave background decay. But should discrepancies appear, subtle differences between predicted and observed energy loss, they could hint at mechanisms beyond conventional physics, perhaps signatures of accelerated cooling, or of forces acting to siphon energy from the cosmos more efficiently than expansion alone allows. Meanwhile, the European Space Agency's Euclid mission complements Webb's gaze by mapping the distribution of dark energy across billions of galaxies. Dark energy, the enigmatic force driving the universe's accelerated expansion, may be intimately tied to cooling mechanics. By tracing its influence on cosmic structure, Euclid provides a large-scale laboratory for understanding how the universe's expansion might amplify temperature decline. Ripples in the expansion rate, variations in galaxy clustering, and subtle distortions of space-time itself all serve as clues. Each measurement offers the possibility of connecting the macroscopic motion of the cosmos with the microscopic decay of photons, revealing whether cooling is simply a passive process or something more insidious, more active, lurking in the background of space-time. Closer to the quantum frontier, the Ice Cube Neutrino Observatory in Antarctica listens to the universe's faintest messengers. Neutrinos, nearly massless and nearly imperceptible, travel unimpeded through galaxies, stars, and planets, their trajectories preserved across cosmic distances. These ghostly particles carry information about high-energy events and thermal processes across the cosmos. By tracking their energy spectra, arrival rates, and distribution, IceCube can provide indirect evidence of energy dissipation mechanisms. Should neutrinos arrive with anomalies in expected energy loss, it might suggest that cosmic cooling is not a uniform, passive drift but has hidden accelerants at work, forces capable of draining energy from ordinary matter or altering the propagation of radiation across space. At the smallest scales, physicists turn to the Large Hadron Collider, seeking to understand the stability of the vacuum itself. If the universe resides in a false vacuum, a metastable energy state, then the decay of this state could be intimately tied to accelerated cooling. High-energy collisions recreate conditions analogous to the early universe, probing the scalar fields and quantum fluctuations that could, in theory, precipitate a false vacuum collapse. By observing particle interactions, rare decay channels, and symmetry violations, scientists can place limits on the likelihood of catastrophic vacuum transitions. Each measurement constrains the possible mechanisms by which temperature and energy might decline more rapidly than passive expansion predicts, tying the microcosm of particle physics to the grand arc of cosmic evolution. Together, these instruments form a network of cosmic thermometers, stretching from the smallest particles to the largest structures, from the first photons emitted after the Big Bang to the present moment. The search is both observational and theoretical, requiring the meticulous comparison of data with models grounded in general relativity, quantum mechanics, and cosmology. Scientists ask, do photons lose energy simply through expansion as predicted by cosmological redshift, or is there an additional sink, a hidden hand drawing energy from the universe in ways yet unseen? Each observation adds a pixel to a picture of the universe in motion, a universe whose cooling may be gentle or driven, predictable or mysterious, passive or actively accelerating. The philosophical stakes are profound. If cooling is purely passive, the universe's fate is a quiet one, a gradual fade into darkness, a drift toward entropy and silence. But if observations reveal active processes, if phantom energy, false vacuum decay, or other unknown mechanisms are at work, the cosmos may be racing toward its end, its cold accelerated by forces beyond ordinary intuition. Detecting this would reshape not only our understanding of physics but our conception of the universe's temporal narrative. The cosmos would not merely age and dim, it would be subject to forces capable of accelerating its thermal demise, forces that render the final silence not inevitable but orchestrated by the underlying fabric of reality. The search is ongoing. Webb and Euclid probe the vastness of space, IceCube listens to particles that have crossed cosmic time, and the LHC teases the vacuum of space itself for signs of instability. Together, these efforts form a symphony of inquiry, a careful and poetic attempt to hear the mechanics behind the universe's falling temperature. Each photon, neutrino, and collision carries a note in this cosmic score, and scientists are learning to read the faint melody encoded within. The redshift of distant galaxies, the distribution of dark energy, the behavior of fundamental particles. These are the signatures that may reveal whether the universe's cooling is a passive sigh of expansion or the manifestation of hidden, accelerating forces that guide the cosmos toward extremes beyond our comprehension. In contemplating these experiments, one cannot escape the quiet poetry of the enterprise. Humanity reaches across space and time to measure the fading warmth of a universe older than imagination, to detect processes invisible to ordinary perception. The universe, in its vastness, communicates through subtle shifts in wavelength, through minute variations in particle energies, and through the distribution of matter across cosmic voids. Each signal is a whisper of its thermal story, a trace of its journey from the fiery birth of the Big Bang to the cold, silent horizon of ultimate entropy. Ultimately, the search to detect cooling mechanics is a testament to the audacity of science and the reflective depth of human curiosity. By probing the earliest photons, mapping dark energy, tracking ghostly neutrinos, and testing the stability of the vacuum, scientists seek to determine whether the universe's decline into cold is an inevitable drift or a more active, accelerated process. They chase the subtle, the extreme, and the nearly imperceptible, seeking to understand not just the rate of cosmic cooling but the forces that may be orchestrating it. In this endeavor, observation and speculation converge, and the quietest temperature of all, the universe's ultimate cold, becomes both a measurable phenomenon and a profound philosophical mirror, reflecting the fragility, vastness, and ultimate mystery of existence. As the universe drifts toward its final eons, the profoundest silence begins to settle, not merely the absence of heat or light, but a metaphysical quiet, a stillness that resonates beyond physical measurement. In this final stage, the cosmos becomes a place without observers, a reality in which nothing exists to witness the dance of particles or the slow decay of photons. Without observers, the rules of quantum measurement, which collapse potential into actuality, lose their stage. Superpositions remain unobserved, possibilities uncollapsed, and the universe itself drifts into a state of indeterminate being. The universe, once vibrant with interactions, becomes a realm of potentialities suspended in perpetual ambiguity. In the early 20th century, Einstein expressed a profound concern about the meaning of reality in the absence of observers. He worried that without sentient beings to measure and contextualize events, the universe might lose coherence, a cosmic theater without an audience. Hawking later offered a counterpoint, that meaning does not depend upon consciousness, that reality persists, unfolding according to its own laws, indifferent to whether any mind witnesses its course. Yet in the context of ultimate cooling, the interplay between observation and existence gains a poetic resonance. The fading heat, the dispersal of matter, the evaporation of stars, and the eventual evaporation of black holes combine to create a cosmos without active measurement. Coldness becomes a symbol of non-interaction, a manifestation of a universe in which consequences themselves are muted by the absence of gradients. Energy gradients, the flow of heat, the cascade of photons through interstellar space. These are the mechanisms by which the universe communicates with itself. Life, observers, and processes create feedback loops, instilling the cosmos with interaction and meaning. But in a universe that has reached the degenerate era and beyond, stars have burned out, galaxies have faded, and particles drift apart beyond causal contact. Observers vanish. Without gradients, there is no action, no reaction, no thermodynamic asymmetry to mark the passage of time or the unfolding of events. The universe exists, yet it exists as a passive structure, indifferent and unmeasured, a space of frozen potential and quieted consequence. In this ending, cold becomes more than a physical parameter. It becomes a metaphor for a universe that has ceased to affect itself. In the absence of observers, a photon may continue to traverse intergalactic voids, stretched by cosmological expansion, but its journey holds no interaction, no imprint on matter or consciousness. Every particle, every wave, every residual fluctuation moves without consequence, unrecorded, unremembered. The laws of thermodynamics continue to operate in principle, but without observers, the informational aspect of reality, the encoding of energy, the causal chain of events, loses practical significance. Entropy may still increase, yet in a cosmos without measurement, entropy becomes a mathematical abstraction rather than a narrative of evolving disorder. Philosophically, this ending mirrors the notion of thoughtlessness. Consciousness, awareness, and observation are the mechanisms by which reality acquires relational meaning. Without them, space and time persist as empty scaffolds, vast and silent. Gradients flatten, interactions cease, and the universe reaches a state of ultimate indifference. Matter and radiation may continue to exist, but in isolation so profound that no wave of influence crosses the void. Black holes have evaporated, their stored entropy dispersed as faint radiation, yet even this energy drifts without an audience. The universe becomes a system of potentialities, unmeasured and unresolved, a cosmic echo of a mindless state. This stage also challenges our understanding of information. Cosmological horizons now isolate all particles from one another. No observer, no measuring device, no consciousness exists to encode or decode information. Even the faintest whispers of energy carry no meaning. The cooling universe, in reaching near absolute uniformity, becomes a canvas on which the absence of interaction is itself the dominant feature. The ultimate temperature of space, approaching theoretical zero, is not merely a measurement. It is the physical manifestation of a universe devoid of relational events. In this sense, coldness and silence are inseparable, intertwined in a state of final, indifferent stillness. Cosmic thoughtlessness is not merely metaphorical. It is rooted in the laws of physics themselves. Observations of the early universe show that interactions and gradients allow complexity, structure, and life to emerge. Yet as the universe cools and dilutes, the framework that enables consequence collapses. Causal chains weaken as particles drift beyond horizons, rendering physical interaction impossible. Even quantum events, which in the presence of measurement manifest as definite outcomes, remain uncollapsed in a universe without observers. Reality exists in potential, but potential no longer crystallizes into actuality. The universe continues, yet the narrative of existence, the interplay of events, the consequences of action, disappears. In reflecting upon this ultimate fate, the mind cannot help but sense a strange resonance between physics and philosophy. Einstein's concern about meaning finds a poetic echo in the physics of extreme cooling. Hawking's insistence on the independence of reality is true in principle, yet in practical, relational terms, the universe becomes devoid of effect. Coldness becomes synonymous with non-interaction. The universe, in its final epochs, is a realm where the absence of observers mirrors the absence of gradients, a cosmos in which nothing impacts anything else, a space that exists but does not act, a reality stripped of consequence. Ultimately, the cosmic ending that resembles thoughtlessness is a profound meditation on the intersection of physics and philosophy. It is a universe in which cooling, expansion, and isolation converge to create a state in which the very mechanisms that once produced consequence, energy gradients, interactions, observations, have vanished. Silence is no longer metaphorical. It is an ontological condition. Cold is not merely a number on a thermometer. It is the signature of a universe that has ceased to affect itself, a cosmos in which events proceed without consequence, and where the absence of observers renders existence unmeasured, indefinite, and profoundly still. The final lesson, if one can call it that, is the quiet reflection of a universe reaching the terminus of its thermal and informational history. In the extreme, the cosmos illustrates the intimate connection between interaction, observation, and meaning. As cooling approaches its ultimate limit and observers vanish, the universe itself becomes a mirror of non-awareness, a reflection of ultimate indifference. In the profound cold and quiet, the final stage of existence resembles not death in any dramatic sense, but thoughtlessness, the cessation of effect, the end of consequence, the fading of reality into unmeasured potential, a silent testament to the ultimate solitude of spacetime. In the final symphony of the cosmos, the relentless drift toward coldness whispers not only of endings but of beginnings. The universe cools, but in its cooling lies a reflection of its birth. If the ultimate fate is a void of near-absolute uniformity, then heat must have been the primordial spark, the first pulse of existence, the memory of creation itself. Temperature, in this sense, is not merely a physical parameter. It is the universe's autobiography, each degree a line in the story from nothingness to the first atoms, the ignition of stars, the weaving of galaxies. To read the cosmos is to read its thermal history, to feel the fading warmth as the record of its earliest moments slowly dissolves. In the beginning, the universe was hot beyond comprehension. Temperatures soared past billions of Kelvin, a searing ocean in which quarks swam freely and photons collided with impossibly energetic fury. Every particle, every vibration, every photon was a note in the symphony of creation, encoding the laws of physics in real time, etching the geometry of space and the scaffolding of matter. The cosmic microwave background we measure today, faint and chilling at 2.725 Kelvin, is a ghostly echo of that heat, a memory stretched thin by 13 billion years of expansion and energy dilution. It is a fossil of energy, a remnant of the first light, a lingering whisper of the primordial blaze. Cooling, then, is not a neutral decline. It is memory fading. As photons stretch into undetectable wavelengths, as atomic oscillations slow and stars fade into dead embers, the universe is forgetting itself. Each loss of thermal energy is a loss of historical fidelity, a gentle erasure of the narrative of existence. Matter and radiation no longer interact as they once did, and the once vivid tapestry of cosmic events begins to blur. Entropy has always promised disorder, but here, disorder is not chaos. It is the quiet diminishment of the record, the gradual flattening of all distinctions into uniform stillness. The universe approaches a state in which its own history can no longer be read by any internal observer because the instruments, the clocks, the photons themselves, have lost the energy to carry information. In this perspective, temperature becomes a measure of cosmic lifespan. The fiery youth of the universe, dense and energetic, was its moment of vitality. Cooling marks maturity, senescence, and eventual cessation. The warmth of stars, the radiation of galaxies, the kinetic energy of drifting matter, these were the universe alive, acting, evolving. As cooling accelerates, as heat retreats into memory, the cosmos enacts its own mortality. The fading thermal gradients are the universe's heartbeat slowing, a signal that all processes, all interactions, all consequences, are winding down toward silence. The cold is not merely absence, it is the epitaph of activity, the signature of a life lived across eons. Yet within this narrative of decay lies profound revelation. If coldness is the final state, then heat is the ultimate proof of the universe's inception. Heat was the medium through which particles discovered each other, through which gravity sculpted filaments of matter, through which light traveled across darkness, illuminating the first structures. Temperature encodes causal chains, the successive unfolding of events from the earliest quark-gluon plasma to the first neutral atoms, from the ignition of stars to the rise of galaxies. In this way, cooling is more than a physical trend. It is a mirror held to the cosmos, revealing the initial conditions that made existence possible. The thermal history of the universe becomes a metaphor for memory itself. The further the cosmos drifts into cold, the more abstract and distant its origins become. The photons that once carried immense energy now stretch across incomprehensible distances, their wavelengths swollen beyond recognition, carrying with them only a whisper of information. The heat of creation has been diluted into near invisibility, but the imprint remains. In the extreme cold, the universe retains only the faintest echo of its beginning, a cosmic mnemonic, the first instant frozen in the final darkness. This reflection on origins is not merely scientific, it is philosophical. The narrative of heat and cooling reveals a symmetry between creation and cessation. The searing energy of the Big Bang was the universe alive, writing its own story. The creeping cold of the distant future is the universe closing that story, folding memory into uniformity. Just as life traces its beginning in its initial burst of activity and ends in the gradual decay of energy and function, the cosmos traces its birth in heat and marks its mortality in cold. Temperature, here, is both timeline and witness, a ledger of existence that begins at ignition and fades toward irrelevance. The final lesson of this cooling is a meditation on permanence and transience. While the universe will eventually reach a state where gradients vanish, interactions cease, and time itself becomes unmeasurable, the memory of heat remains embedded in the physical structure of reality. Galaxies, now silent and dark, were once forged in stellar furnaces. Cosmic radiation, though stretched to undetectable wavelengths, carries the imprint of its violent origins. The universe, in cooling, does not annihilate its past. It compresses it into the faintest whispers, echoes so delicate that they may persist even when energy ceases to move. In this sense, the end state of the universe is not a void of nothingness, but a silence imbued with the memory of beginnings. The final cold is a reflection of the first warmth. Entropy has erased the intermediate drama, but the origin remains encoded, subtle, and resilient. The fading temperature acts as a bridge across cosmic time, linking the incomprehensible intensity of the Big Bang to the near-absolute stillness of the distant future. In studying cooling, scientists glimpse not only the fate of all matter and radiation but the story of the cosmos itself, a narrative in which every degree lost is a reminder of the heat that once defined existence. Ultimately, the cooling universe speaks to a profound truth: mortality, memory, and origin are intertwined. The universe's temperature is its lifespan, heat its initial vitality, and coldness the fading of that vitality into eternity. What remains after the final tick of atomic clocks, after the last photon stretches beyond recognition, is the echo of the first moment. All that follows becomes still, unmeasured, silent, yet forever bearing the imprint of the fire from which all things emerged. The universe, in losing heat, is not merely dying. It is remembering its own birth in the language of fading warmth, a final meditation on the origin of all things written in the universal ledger of energy and time. In the final symphony of the cosmos, the relentless drift toward coldness whispers not only of endings but of beginnings. The universe cools, but in its cooling lies a reflection of its birth. If the ultimate fate is a void of near-absolute uniformity, then heat must have been the primordial spark, the first pulse of existence, the memory of creation itself. Temperature, in this sense, is not merely a physical parameter. It is the universe's autobiography, each degree a line in the story from nothingness to the first atoms, the ignition of stars, the weaving of galaxies. To read the cosmos is to read its thermal history, to feel the fading warmth as the record of its earliest moments slowly dissolves. In the beginning, the universe was hot beyond comprehension. Temperatures soared past billions of Kelvin, a searing ocean in which quarks swam freely and photons collided with impossibly energetic fury. Every particle, every vibration, every photon was a note in the symphony of creation, encoding the laws of physics in real time, etching the geometry of space and the scaffolding of matter. The cosmic microwave background we measure today, faint and chilling at 2.725 Kelvin, is a ghostly echo of that heat, a memory stretched thin by 13 billion years of expansion and energy dilution. It is a fossil of energy, a remnant of the first light, a lingering whisper of the primordial blaze. Cooling, then, is not a neutral decline. It is memory fading. As photons stretch into undetectable wavelengths, as atomic oscillations slow and stars fade into dead embers, the universe is forgetting itself. Each loss of thermal energy is a loss of historical fidelity, a gentle erasure of the narrative of existence. Matter and radiation no longer interact as they once did, and the once vivid tapestry of cosmic events begins to blur. Entropy has always promised disorder, but here, disorder is not chaos. It is the quiet diminishment of the record, the gradual flattening of all distinctions into uniform stillness. The universe approaches a state in which its own history can no longer be read by any internal observer because the instruments, the clocks, the photons themselves, have lost the energy to carry information. In this perspective, temperature becomes a measure of cosmic lifespan. The fiery youth of the universe, dense and energetic, was its moment of vitality. Cooling marks maturity, senescence, and eventual cessation. The warmth of stars, the radiation of galaxies, the kinetic energy of drifting matter, these were the universe alive, acting, evolving. As cooling accelerates, as heat retreats into memory, the cosmos enacts its own mortality. The fading thermal gradients are the universe's heartbeat slowing, a signal that all processes, all interactions, all consequences, are winding down toward silence. The cold is not merely absence, it is the epitaph of activity, the signature of a life lived across eons. Yet within this narrative of decay lies profound revelation. If coldness is the final state, then heat is the ultimate proof of the universe's inception. Heat was the medium through which particles discovered each other, through which gravity sculpted filaments of matter, through which light traveled across darkness, illuminating the first structures. Temperature encodes causal chains, the successive unfolding of events from the earliest quark-gluon plasma to the first neutral atoms, from the ignition of stars to the rise of galaxies. In this way, cooling is more than a physical trend. It is a mirror held to the cosmos, revealing the initial conditions that made existence possible. The thermal history of the universe becomes a metaphor for memory itself. The further the cosmos drifts into cold, the more abstract and distant its origins become. The photons that once carried immense energy now stretch across incomprehensible distances, their wavelengths swollen beyond recognition, carrying with them only a whisper of information. The heat of creation has been diluted into near invisibility, but the imprint remains. In the extreme cold, the universe retains only the faintest echo of its beginning, a cosmic mnemonic, the first instant frozen in the final darkness. This reflection on origins is not merely scientific, it is philosophical. The narrative of heat and cooling reveals a symmetry between creation and cessation. The searing energy of the Big Bang was the universe alive, writing its own story. The creeping cold of the distant future is the universe closing that story, folding memory into uniformity. Just as life traces its beginning in its initial burst of activity and ends in the gradual decay of energy and function, the cosmos traces its birth in heat and marks its mortality in cold. Temperature, here, is both timeline and witness, a ledger of existence that begins at ignition and fades toward irrelevance. The final lesson of this cooling is a meditation on permanence and transience. While the universe will eventually reach a state where gradients vanish, interactions cease, and time itself becomes unmeasurable, the memory of heat remains embedded in the physical structure of reality. Galaxies, now silent and dark, were once forged in stellar furnaces. Cosmic radiation, though stretched to undetectable wavelengths, carries the imprint of its violent origins. The universe, in cooling, does not annihilate its past. It compresses it into the faintest whispers, echoes so delicate that they may persist even when energy ceases to move. In this sense, the end state of the universe is not a void of nothingness, but a silence imbued with the memory of beginnings. The final cold is a reflection of the first warmth. Entropy has erased the intermediate drama, but the origin remains encoded, subtle, and resilient. The fading temperature acts as a bridge across cosmic time, linking the incomprehensible intensity of the Big Bang to the near-absolute stillness of the distant future. In studying cooling, scientists glimpse not only the fate of all matter and radiation but the story of the cosmos itself, a narrative in which every degree lost is a reminder of the heat that once defined existence. Ultimately, the cooling universe speaks to a profound truth: mortality, memory, and origin are intertwined. The universe's temperature is its lifespan, heat its initial vitality, and coldness the fading of that vitality into eternity. What remains after the final tick of atomic clocks, after the last photon stretches beyond recognition, is the echo of the first moment. All that follows becomes still, unmeasured, silent, yet forever bearing the imprint of the fire from which all things emerged. The universe, in losing heat, is not merely dying. It is remembering its own birth in the language of fading warmth, a final meditation on the origin of all things written in the universal ledger of energy and time. In the stillness of the cosmos, the narrative of existence comes full circle, returning to the photon that once blazed with unimaginable energy, now stretched across millions of kilometers, drifting in a quiet so absolute it borders on the incomprehensible. This is a photon that has witnessed the birth and death of galaxies, the ignition and fading of stars, the slow unraveling of matter into lonely, drifting atoms. Its wavelength has lengthened beyond measure, its energy diminished to a whisper of what it once carried, incapable of warming even the tiniest dust grains suspended in the darkness. Yet within this subtle trace lies the entirety of cosmic memory, a testament to creation and decay entwined in the same spectral thread. The universe began in a state of furious energy, a searing blaze where every particle collided, every photon resonated, every wave vibrated with purpose. From this chaotic infancy, matter coalesced into structures of staggering scale, galaxies spiraling with silent grace, stars igniting as furnaces of nuclear fusion, planets emerging from cosmic dust. Temperature, the measure of energy, was the metric of life, motion, and consequence. Warmth was creation's signature, the indelible mark of a universe alive and expanding. But as expansion continued, as the relentless march of time stretched space itself, energy became diluted, gradients flattened, and the vibrant tapestry of interactions slowly unraveled. Now, in this late era, the universe is neither chaotic nor turbulent. It is quietly, unrelentingly cold. Heat has been dispersed, absorbed into the vast emptiness between stars, between galaxies, between particles so far removed from each other that interaction is no longer meaningful. The very mechanisms that once allowed work to be performed, that allowed chemical reactions and life and motion, have decayed. Galaxies have faded into darkness, stars have exhausted their nuclear fuel and cooled into black dwarfs, white dwarfs, or evaporated entirely into radiation that will stretch into near invisibility. Even black holes, once thought eternal, have evaporated through Hawking radiation, leaving only a thin mist of particles drifting in a universe growing ever more sparse and silent. One cannot help but ask, why did the universe not remain warm? Why did it not preserve its energy, its capacity for interaction, for consequence? Why must everything fade? The answer lies in the inevitability of thermodynamics, in the ceaseless march toward equilibrium. Entropy ensures that gradients, those essential differences in energy that power motion, chemistry, and life, cannot persist indefinitely without input. Without new sources of energy, without mechanisms to reverse the cooling, the cosmos must approach uniformity. The universe, in its wisdom or inevitability, has no need to defy its own rules. It cools not out of malice or neglect but because that is the path dictated by the fundamental laws governing all matter and radiation. Yet there is a paradoxical beauty in this decay. In the fading of energy, the universe becomes a meditation on inevitability and reflection. The very act of cooling is a process of storytelling, of history being written in the language of diminishing photons and stretched wavelengths. Each photon, each particle, each wave carries with it the memory of processes that have long ceased. The temperature of the cosmos, approaching absolute uniformity, is a ledger of all that has transpired. Every burst of light, every supernova, every collision of galaxies is encoded in the residual radiation that still exists, however faintly. Coldness, in this sense, is not the absence of meaning. It is the quiet preservation of the memory of heat, the fading echo of a universe that once roared with activity. Consider the implications for perception, for consciousness, for reflection itself. In a universe without sufficient energy gradients, no chemical reactions can occur, no photons can excite neurons, no particles can carry signals across distances sufficient to constitute observation. The cosmos has reached a state of non-interaction. Existence continues, but there is no one to witness it, no system capable of perceiving or interpreting it. The fading heat, the absence of energy, becomes synonymous with the absence of narrative. The universe, once a dynamic story, becomes a silent manuscript, its pages spread across infinity, inked in energy now almost entirely dissipated. Even as the cosmos cools into the faintest remnants of radiation, there is profound poetry in this quietude. The photon that now drifts across light years with negligible energy is a symbol of continuity, a bridge connecting the explosive brightness of creation to the subtle quiet of finality. It embodies the duality of existence, beginning in extraordinary intensity, ending in near nothingness, yet persisting across time in a form that can still be recognized as part of the cosmic continuum. The universe's life cycle is written not only in matter and motion but in energy, in temperature, in the very ability to do work. In this light cold is not mere emptiness. It is the final form of memory, a relic of creation rendered subtle, abstract, and almost unmeasurable. This reflection invites a broader contemplation. What does it mean for a universe to end? Not with fire, nor with catastrophe, nor with abrupt collapse, but with gradual, inexorable cooling. A universe in which nothing remains sufficiently energetic to cause change is a universe that has exhaled its breath into eternity. It is a cosmic sigh, a quiet resignation to the laws that govern all that exists. The cessation of thermal gradients signals the cessation of consequence. Causality persists only as the shadow of former activity. Interaction has ceased, and with it, the dynamic processes that once defined reality. Yet this ending is not tragic. There is no suffering inherent in uniform cold, no malice in the fading of photons, no loss in the absence of observers. It is inevitable. The universe is not cruel. It is simply following the trajectory set by its own physics. The dissolution of heat into silence is a natural consequence of expansion, thermodynamic law, and the finite energy of creation. To witness this truth is not to mourn but to understand, to perceive the profound inevitability that underlies all existence. There is dignity in this process, a quiet elegance in the predictable arc from blazing youth to serene stillness. The final photon, stretched and cold, drifting alone across a space-time now vast beyond comprehension, is a messenger of this inevitability. It carries with it the faint imprint of galaxies that have long collapsed into darkness, stars that have burned out, and matter now dispersed so thinly that interaction is impossible. Its energy is negligible, yet it remains. It is the universe's memory, the last testament to the processes that once animated space with color, heat, and light. It is a symbol of continuity in the midst of inevitable cessation, a reminder that the universe has always been and always will be a chronicle of transitions, of beginnings fading into endings. As this reflection closes, one is left with the sense of the universe as a cosmic breath, inhaled in the blazing fire of the Big Bang, exhaled into the frozen silence of its far future. Heat was the pulse, energy the heartbeat, motion the rhythm, and now, in the extreme cold, all movement slows to imperceptibility. Time itself, measured by change and energy exchange, becomes nearly meaningless. The universe, in losing warmth, has lost the capacity to register its own progression. It exists in a state of frozen memory, a silent testimony to all that has transpired. And so the final meditation arises. The universe began with roaring brightness and ends dissolving into a silence colder than thought. Not tragic, not cruel, not mournful, but inevitable. The laws of physics have guided this grand narrative from inception to ultimate cooling, from heat to near-zero energy, from observable consequence to universal quiet. In this contemplation, one perceives a cosmic arc, a story that spans eons, a reflection of origins in the very act of ending. In the end, the universe whispers its final truth. It is a tale written in photons stretched across unimaginable distances, in radiation that can barely move, in particles too isolated ever to interact again. The cosmic ledger closes, the last clocks tick slowly toward invisibility, and the last gradients flatten into uniformity. A single breath of energy, exhaled into the vastness of eternity, until nothing remains warm enough to remember it existed. This is the final act of the universe. A universe that spoke, that shone, that acted, and now rests. The cooling is complete, and in the pervasive cold, one understands the profound symmetry of existence. Birth and death, heat and cold, memory and forgetting, all are intertwined in the timeless fabric of reality. The cosmos has returned to silence, and in that silence, the echo of its fiery beginnings endures, subtle, nearly imperceptible, yet eternal.